Imagine a classroom bustling with students. The teacher, Ms. Johnson, needs to find a particular student. Let's call him Alex. The challenge lies in finding Alex efficiently. How Ms. Johnson approaches this seemingly simple task can be analyzed through the lens of time complexity. In computer science, time complexity measures the efficiency of an algorithm. It quantifies how the execution time of an algorithm increases as the input size grows. In our classroom analogy, the input size is the number of students. Let's explore different search strategies and their corresponding time complexities. Ms. Johnson asks each student to search for Alex individually, meaning each student asks every other student if they are Alex. This leads to repeated questions and interactions, making the process time-consuming. In the worst-case scenario, each of the n students asks n others, making it very lengthy. This results in a time complexity of O(n)(2), meaning time grows quadratically with the number of students. For hundreds of students, the interactions would be overwhelming and impractical. A more efficient approach would be for Ms. Johnson to simply call out Alex's name and ask him to identify himself. In this scenario, Ms. Johnson only needs to perform one action for each student, calling their name. This method has a time complexity of O(n), pronounced order n. The number of operations grows linearly with the number of students. If there are twice as many students, it will take roughly twice as long. O(n) algorithms are generally more desirable than O(n)(2) algorithms, especially for larger input sizes. Section 4. Divide and conquer. The power of O log n. Imagine needing to find a specific student quickly. If students are seated alphabetically, we can use a more efficient search method. Ms. Johnson could use a divide and conquer approach, like a binary search. She asks the middle student if they are Alex. If not, she eliminates half the class based on alphabetical order. This process continues until Alex is found. This strategy has a time complexity of O log n, very efficient for ordered data. Logarithmic functions grow slower than linear ones, making O log n ideal for large data sets. Section 5. Big O notation, a measure of efficiency. In all our scenarios, we used Big O notation to describe the time complexity. Big O notation provides an upper bound on the growth rate of an algorithm's runtime. It focuses on the most significant terms and ignores constant factors. For instance, an algorithm with a runtime of 2n plus 5 would still be considered O(n). Big O notation allows us to compare the efficiency of different algorithms without getting bogged down by implementation details. Section 6. Time complexity versus actual time. It's important to note that time complexity doesn't measure the actual time an algorithm takes to run. Instead, it provides a theoretical framework to understand the efficiency of an algorithm. The actual execution time can be influenced by factors such as hardware. A faster computer will naturally execute code faster. The type of processor, amount of RAM, and storage speed all play crucial roles. Network conditions. Network latency can impact algorithms that rely on data transfer. Slow or unstable connections can significantly delay execution. Implementation details. Even with the same time complexity, different implementations can have varying runtimes. Code optimization and programming languages can make a difference. Time complexity focuses on the rate at which the runtime grows as the input size increases. It helps predict performance for large inputs. It provides a standardized way to analyze and compare the efficiency of algorithms. Understanding both time complexity and actual execution time is essential for optimizing performance.